So in this tutorial, we're going to look at the law of reflection and see how it applies to mirrors as well as regular objects. It is a fairly simple concept, but there's a little bit of subtlety to it, so pay close attention. Also, it will be convenient to have a straight edge or a ruler nearby because we're going to be doing ray diagrams, very simple ones, but it's really helpful to be able to draw a straight line. So the reason we're doing that is we are going to represent waves in a different way. You don't have to write this, but normally we can represent a transverse waves like that, let's say light. Or we can look at light as ripples rippling out from a source, like a light bulb. But a more convenient way of representing how light travels is something called a ray. Okay, and hence a ray diagram. And a ray shows a few things. It shows a direction of wave travel. Okay, at least one part of a wave. And the rule is, so if let's say we have, let's see here, a source of light, a dot, and we can look at the wavelengths every so often. So we can say that the waves travel out in concentric circles, propagating out, getting bigger and bigger and bigger. Okay, or we can say the direction of wave travel, we can represent it with an arrow like this, or like that. And what we see, those rays we're drawing there, in general, are always perpendicular to the wavefront. Okay, so if I were to draw a ray of light, you could draw the circles around it such that they are perpendicular to that ray. Okay, so let's look at reflection right now and the general schematic of that. So we have a ray of light coming in from the upper left corner and it's moving down to the right. So this is one particular part of the wave, and it hits a medium right here called medium 2, and it's starting in some medium 1. When it hits that, a number of things can happen. What we're interested in here right now is reflection. It's going to bounce off that surface very simply. But it's not going to bounce off in any random fashion. It follows a certain rule. It's called the law of reflection. And the law of reflection is fairly simple. So if I get if I draw a line here, so I'm going to use this tool, what I'll find is that the ray that goes out, and you might want to follow me first before, or watch first before you do it, is something like that. And if you look at the reason I chose that angle that reflects, it's such that this angle and that angle should be the same. All right, so I'm looking at it. They're not perfect, but it's close enough. So we labeled the angles two different ways. This is called theta I. Theta I simply means the incident angle. Okay, the angle that it comes in. And then the angle that it goes out is called theta R, which is, makes sense, the reflected angle. Okay, and so we can go below and say the law of reflection. Very, very straightforward. All right, the angle of incidence equals the angle of reflection. And that's always true of any wave, not just light. And here's the key thing, though. Notice where I marked the angles. It wasn't with the surface. You can't do that. That's not allowed. Okay, you lose points that way. I'll explain why later. It's measured something called the normal, relative to the normal. If you're not willing to draw normal when we're drawing rays for reflection and then ultimately refraction, that's going to create problems for you in terms of losing points. So the reason that so this is the normal right here, this dashed line. Okay, so we have a surface. The reason we draw normal is if I had a curved surface and I had a ray coming in like that, well, you can't really measure that angle very well. But you can always draw a normal, which normal means perpendicular to the surface. So when I draw that dashed line, it's perpendicular to that spot right there. Then that angle I can measure very nicely, and then I can draw a ray that's on the opposite side of that normal. And that shows the law of reflection for, let's say, a curved surface. So for flat surfaces, you can get away with measuring with the surface, but if you label things incorrectly, in other words, not with normal, you lose points on the test. Okay, so we'll be doing stuff with that as an activity in class. So let me talk about two basic types of reflection and how they're useful to understand. The first one is called a diffuse reflection. Okay, and that's when waves strike an uneven surface, a rough surface, which is most surfaces. And so when we hit a rough surface, let me just see if I have this on the other page. I do, and I'll show you this. So actually, I'll go to right here. So why don't you turn the other side? So let's say this represents a bumpy surface, which most things are. I have 3 parallel rays of light coming in. Well, even though they're coming in parallel, they're not going to go out parallel because the surface isn't perfectly smooth. So if I want to draw the 3 reflected rays, I got to be a little bit careful. You're not just going to eye it up and draw rays. You got to take a approach. So if I look at this one, it's going to hit right about here. So what I want to do at that point is draw a normal. So I'm going to approximate right now. I'm not going to get a protractor out, even though we will eventually be doing that. I'm going to draw a little dashed line that's roughly perpendicular to the surface. So there's my incident angle. The law of reflection says that the reflected angle has to be the same angle, but on the other side of the normal. So I would draw a reflected ray like this, and it might hit the surface again. I'm not going to worry about that. So there's the first reflected ray. And the second one, my normal is easier to draw, perpendicular to the surface right here. So here's my incident angle. So my reflected angle is going to be out at the same angle, something like that. And then in this third case, my normal is like that. I have a large incident angle, so I'm going to have a large reflected angle. And so in diffuse reflection, parallel rays come in, but the light scatters in all directions. And if we were to fill in all the other rays between here and here, we would see that light would go every which way. So that has actually use. That's actually pretty important. Okay? It is the basis. Sorry, this got shifted. It is the basis for our ability to see objects. Okay? That's the basis for sight. Think about anything you're looking at. You're looking at an object. Look at your hand in front of you. Your ability to see it in front of you is because light from somewhere in your house, if the sunlight is hitting your hand, and it is reflecting off of it. And it's not reflecting off it in just one direction. It's reflecting off in many, many different directions so people can see your hand from many, many different angles. Without that reflection off, that diffuse reflection, you would not be able to see anything. Now, in contrast to diffuse reflection is called regular reflection. And regular reflection is when it strikes a smooth surface, a very, very smooth surface. In other words, a mirror. Okay, and that's what makes mirrors mirrors, is that the surfaces are very, very smooth. And they are reflected in a very ordered manner. In other words, if they come in parallel, they'll go out parallel. And this is the basis for all mirrors. The best mirrors in nature is water. Flat water is still water, I should say. When there's no ripples in a pond or lake, they make excellent mirrors. In manufactured mirrors, it's all about a glass usually, because glass can be made very, very smooth. So on this diagram, if I've got 2 parallel rays coming in, if I draw a normal here, here's my incident angle. I'm going to draw a reflected angle on the opposite side of the normal, and then I do the same thing here, and they come in parallel. They should go out parallel. And because of that, for reasons we'll see a little bit, you can get images formed, mirror images formed. That's pretty important. We'll discuss the details of that. Okay, so to finish up here, let's look at some quick little problems. All right. So it says an angle between incident ray of light and reflected ray of light is 84 degrees. What is the incident angle? Okay. There's not a lot of space here, but it might be helpful to draw a little diagram. So here's a surface. I'm going to draw normal because that's important. And so I'm now going to put in my incident ray and then my reflected ray. And I know that the angle between them is 84 degrees. When you draw that and you match 84 to the right spot, then this is easy. We can see that theta I, okay, incident angle is going to be half of that, or 42 degrees. Right? Next one, an incident ray makes a 35-degree angle with the surface of a mirror. What is the angle of reflection? Again, something you're probably doing on the top of your head. All right, so we've drawn our normal, and now let's fill in the information. So it makes a 35-degree angle with the surface. So the tempting thing to say is the angle of reflection is going to be 35 degrees. And hopefully recognized by now that's not right, because it's got to be with the normal. So while that angle is true, the correct angle is 55 degrees. So our incident angle is also 55 degrees. So theta R equals 55 degrees. We've done number 3 already. So one last one, because we want to understand the reflection not only happens off of smooth surfaces, flat surfaces, or even rough surfaces. It can happen off of curved surfaces. So here I've drawn a curved surface that is concave on one side, convex on the other. And we want to understand how this is going to reflect. So you just got to be able to draw a normal at each place. So at this spot right here, I'm going to try to approximate a line that's perpendicular. I've done an okay job. Here's my incident angle. So my reflected angle is going to be something like that. And this side, when it comes in, looks like this. So here's my incident angle. It's going to reflect by that. So we see that the light spreads out when it comes in from a convex side. And if I do the same thing here, the light comes in. Okay. And this one is not perfect, but here is the normal. It's going to do something like that. And then here is the normal at that spot, and it's going to reflect like that. So when it hits a concave side, it converges. And that has very, very important implications, which we'll explore in class. Okay, that's it for now.